11.2 Permutations and Combinations. So in these notes, we're going to expand on what we talked about with the fundamental counting principle in 11.1. So we're going to find the number of ways to order objects, both when order does and does not matter. So instead of thinking about how many possibilities there are, we're going to look at how many ways we can choose a certain number of objects out of a total. So the difference between a permutation and a combination is that with permutations, the arrangement of the objects in a certain order matters. So, for example, choosing first, second, and third place. In a combination, the selection of objects with no order. There's the order that they stand does not matter. So, for example, choosing any 3 people out of 5. You know, ABC is the same as BAC is the same as CAB. The actual order of the objects doesn't matter. So for example, we're going to look at how many ways to choose 2 out of the letters A, B, C, D. And we're going to do this as a permutation and as a combination. So as a permutation, where order matters, let's just think about all the different ways to order these. We're choosing 2 letters out of A, B, C, D. Well, if we start with A, we could have AB, AC, and AD. Then we do that for each letter. BA, BC, BD, CA, CB, CD, and DA, DB, DC. So there are 12 ways to choose 2 letters out of the letters A, B, C, D when order matters. Now as a combination, when order doesn't matter, that means AB is the same as BA. So let's think about this one. Let's start with the A's again. AB, AC, AD. But now when we move on to B, BA, that's the same as AB because the order doesn't matter. It's just an A and a B. So we're going to skip it and go to BC and BD. And then for C's, I already have CA and CB, so we just have CD. And then for D, I already have all the letters. I have DA right here, DB, and DC. So this is it. There's 6 ways if order doesn't matter. So because permutations will always have more ways to do it than combinations because the order matters. All right, for another example here, we have Diego, Caden, and Kyle. They finished a group project. 2 of them have to present to the class. So we'll find this as a permutation where it matters who presents first and second, and as a combination where order doesn't matter, any 2 of them will work. So first we can have Diego and Caden, and Diego and Kyla. If Diego goes first. Let's say if Caden goes first, we could have Caden and then Diego, or Caden and Kyla. And let's say if Kyla goes first, we could have Kyla, Diego, Kyla, Caden. So there are 6 ways to choose 2 out of these 3 people if order matters, what order they present first. So as a combination where order doesn't matter, well, we have Diego and Caden, and Diego and Kyla. We have Caden and Kyla, but I already have Caden and Diego. And then for Kyla, I already have Caden and Kyla and Diego and Kyla. So this is it. There's just 3 ways. So far, the combinations have had half as many options. Now, there is, of course, a formula for this. So when choosing R objects out of n total options, for a permutation, when order matters, so we write that as NPR. We have the total on this side, and the number we're choosing on the right side. The formula is n factorial, the total factorial, over n minus r factorial. So in math, that exclamation mark indicates a factorial, where we multiply a number by all of the numbers smaller than it. So 5 factorial is 5 times 4 times 3 times 2 times 1. Now a combination is the same formula, and it's written NCR, but we also have an extra R factorial in the bottom. So that cancels out all those extra combinations where they're the same objects but in a different order. The combination will eliminate them because the order doesn't matter. So we're going to decide whether we have a permutation or a combination here and then find the answer. So we're going to figure out how many ways to choose these objects. So we have 6 students randomly chosen from a class of 25. Now this is a combination. It doesn't matter what order they're chosen. In this scenario, just any 6 students. So we have 25 choose R, so choose 6, so 25C6 here. And this is going to be 25 factorial over, now n minus R, 25 minus 6 is 19 factorial, and then we have 6 factorial as well. So to actually calculate this, what we can do is simplify it a little bit. So 25 factorial is 25 times 24 times 23 and so on, right? 19 factorial is the same way. So what's going to happen is the 19, 18, 17, and so on is all going to cancel out from up there. So what we end up with is 25, 24, 23, 22, 21, 20, all over 6, 5, 4, 3, 2, and 1. So the 19 factorial part canceled out everything below 20 on the top, and then we still have that 6 factorial left over. So now we just have to multiply these together. 25 times 24, 23, 22, 21, 20 gives me 127,512,000. We're going to divide that by 6 times 5 times 4 times 3 times 2 times 1. And it's going to equal 177,100. Now that's kind of the way you'd work that out by hand. A lot of calculators now will do a lot of this work for us. So for example, you can see here this has an n factorial button. We'll use that on the next problem to calculate those factorials for us. But if you didn't have that, you could do it this way. All right, so for example B, we have from those 6 students, choose who will speak first, second, and third. So we're taking 6 students we chose from the 25, so the 25 doesn't matter anymore. But we're choosing who will speak first, second, and third. So what we have to do here is 6, and we're doing a permutation of 3. So we're choosing 3 from the 6, but we have order matters, so we're doing a permutation. And so this is going to be 6 factorial over 3 factorial. A little easier to do this, we can do this by hand. And this might illustrate what happened earlier a little better. So we have 6 times 5 times 4 times 3 times 2 times 1. And then we have 3 times 2 times 1. So if you see what happens, the 3, the 2, and the 1 all cancel each other out. What we're left with is 6 times 5 times 4, which is 120. So from those 6 students, there's 120 ways to choose who speaks first, second, and third. And if I use the calculator just to show this, I could do 6 factorial divided by 3 factorial, and I get 120. Okay, example C says there are 7 dessert options. You get to choose 2. How many ways are there to choose them? Well, this is another combination because I could choose any 2 I want. It doesn't matter what dessert I get first. So we have a 7 with a combination of 2. I think this is assuming that we can't choose the same one twice, although that is sometimes an option, but that's not an option here. Okay, so 7 choose 2, which would be 7 factorial over 7 minus 2 factorial is 5 factorial, and then we have the 2 factorial as well. Now I can use the calculator for this as well. I could do 7 factorial divided by, in parentheses, 5 factorial times 2 factorial, and I get 21. To double check that, these are small numbers, so we can make sure. I'd have 7, 5, forgot 6, so we'll make that a 6, 5, 4, 3, 2, 1, and then we've got 5, 4, 3, 2, 1, and then 2, 1. So again, the 5 factorial cancels out most of that 7 factorial. So I end up with 7 times 6, which is 42, over 2, which is 21. So as long as you type it in correctly, your calculator will do these factorials for you. Okay, 3 prizes are being raffled off. 75 students bought raffle tickets. How many ways can the 3 prize winners be selected? Now, I'm going to say this is a permutation because when you're doing a raffle, if there's 3 prizes, the first person who wins gets to select a prize first if the prizes are different. So for the purposes of this, these notes, we'll assume the prizes are different and it matters who gets chosen first. So we'll do 75 with a permutation of 3. So we're choosing 3 winners from 75. And so what this would be is n factorial, so 75 factorial, that's the total, over 75 minus 3 factorial, which is 72 factorial. Be careful. Our first example, it was 6 and 3 because 6 minus 3 is 3, which is the same number because it was half. So be careful. Make sure you're doing n minus r on the bottom there. But okay, 75 factorial divided by 72 factorial. This is actually a little easier than it seems. And I can type it in, 75 factorial divided by 72 factorial. It gives me 405,150. We'll see if that holds true. Remember, the 72 factorial is going to cancel everything out on top from 72 down. So what I'm left with is 75 times 74 times 73. So let's see if I get the same thing. 75 times 74 times 73. I get 405,150. So even though there's a lot of numbers that we're working with, usually most of them get canceled out and we're left with just a few that we can multiply pretty easily together. But you will always have more to multiply. Your numbers will be larger with the permutations compared to the combinations.